Going to jump into chapter 5 today, just the one section because it's kind of a big section. Sequences, mathematical induction, and recursion. Section 1, sequences. Imagine that a person decides to count his ancestors. He has 2 parents, 4 grandparents, 8 great-grandparents, and so forth. These numbers can be written in a row as this here, 2, 4, 8, 16, 32, 64, 128, etc. To express the pattern of the numbers, suppose that each is labeled by an integer given its row in the position in the row, like here. Well, the number corresponding to position 1 is 2, which equals 2 to the first power. Number in the second position is 4, which is equal to 2 to the second power. For each subsequent position, the corresponding numbers equal to 2 to the individual position's power. For a general value of k, let a sub k be the number of ancestors in the kth generation back. The pattern of computed values strongly suggests the following for each k. A sub k equals 2 to the k. Definition. A sequence is a function whose domain is either all the integers between 2 given integers or all the integers greater than or equal to a given integer. We typically represent a sequence as a set of elements written in a row. In the sequence denoted a sub m plus 1, a sub m plus 2, etc. to a sub n, each individual element, a sub k, is called a term. The k in a sub k is called a subscript or index. M, which may be any integer, is the subscript of the initial term. And n, which must be an integer that is greater than or equal to m, is the subscript of the final term. This notation here with the ellipsis at the end denotes an infinite sequence. An explicit formula or general formula for a sequence is a rule that shows how the values of a sub k depend on k. Define sequences A and B by the following explicit formulas. A sub k equals k over k plus 1. And B sub I equals I minus 1 over I. For k greater than or equal to 1 or I less or greater than or equal to 2. Compute the first 5 terms of both sequences. It's easy to see that for k equals 1, be 1 over 2. And for I equals 2, it would be 1 over 2 as well. And you can see it calculated out. The values of each of both sequences would be the same as shown here. So 1/2, 2/3, 3/4, 4/5, 5/6, etc. As you can see, the first terms of both sequences are the same. In fact, it can show that all terms of both sequences are the same. So compute the first 6 terms of the sequence C, defined as C sub j equals minus 1 to the jth power. For every integer, j equals is greater than or equal to 0. Yeah? Minus 1 to the 0 would be 1. Minus 1 to the first power would be minus 1. Minus 1 to the second power would be 1. And you could see that it would be oscillating back and forth between minus 1 and 1. Even powers of minus 1 equal 1, and odd powers of minus 1 equal minus 1. It follows that the sequence that oscillates endlessly between 1 and minus 1. Find an explicit formula for a sequence with the following initial terms. 1 minus a quarter, 1/9, minus 1/16, 1/25, and minus 1/36. What would you say how the sequence would be defined? Any ideas? If A is, if you call it the sequence A, and it would be A sub k from 1 to infinity, well, the general term of the sequence is start at 1. Observe that the denominator of each term is a perfect square. Thus, the terms can be rewritten as 1 over 1 squared minus 1 over 2 squared, 1 over 3 squared, minus 1 over 4 squared, etc. Now note that the denominator of each term equals to the square of the subscript of that term, and the numerator equals plus or minus 1. Hence, a sub k equals plus or minus 1 over k squared. Also, the numerator oscillates back and forth between plus 1 and minus 1. Plus 1 when k is odd, and minus 1 when k is even. To achieve this oscillation, insert a factor of minus 1 to the k plus 1 into the formula. So there you go. Consequently, an explicit formula that gives the correct first 6 terms is a sub k equals minus 1 to the k plus 1 over k squared. Note that making the first term a sub 0 would have led to the alternative formula, a sub k equals minus 1 to the k over k plus 1 squared. You can check this to see this formula gives the correct first 6 terms. It is convenient to, it is convenient to use a shorthand notation to write some sums. In 1772, French mathematician Lagrange introduced the capital Greek letter sigma to denote the word sum or summation, and define the summation notation as follows. If m and n are integers, and m is less than or equal to n, this symbol here, red, the summation from k equals m to n of a sub k, is the sum of all the terms a sub m, a plus a sub m plus 1, plus a sub m plus 2, all the way up to a sub n. We say that this is the expanded form of the sum, and we can write this out as a sum like this. We call k the index of the summation, m the lower limit, and n the upper limit of the summation. Let a sub 1 equal minus 2, a sub 2 might equal minus 1, a sub 3 equals 0, a sub 4 equals 1, and a sub 5 equals 2. Calculate the following. The sum of a sub k with k from 1 to 5. What would that be? It's just addition. What elements? Well, it would be all the elements 1 through 5. Add them up together, and you get 0. Minus 2 plus minus 1 plus 0 plus 1 plus 2. When the starting index and the ending index are the same, it's just the value of that one element. So it would be a sub 2, which is minus 1. And k from 1 to 2, the sum of a sub 2k. So that's just k times 2 is 2. 1 times 2 is 2. A sub 2 is minus 1. Plus a sub 2 times 2, or 4, is 1. So it's minus 1 plus 1, which is, again, 0. And there you go, in expanded form. The terms of a summation are expressed using an explicit formula. For instance, it is common to see summations such as a sub k, summation of k squared with k from 1 to 5, or this more, the sum of minus 1 to the I over I plus 1 with I from 0 to 8. Compute the sum of k squared with k from 1 to 5. Well, that would be k squared, so that'd be 1 plus 4 plus 9 plus 16 plus 25, which equals what, 77? Something like that. Yeah? Okay. No, 55, I'm sorry. I know it was a double number, I just forgot which one. But, yeah. It's just to expand it out and do the addition. Solve each term for each value of k, and then add those terms up together to get your final result. When the upper limit of a summation is a variable, an ellipsis is used to write the summation in expanded form. So, in expanded form, this little expression here can be written as the value of the first few terms, followed by an ellipsis, followed by the last term in terms of n, because the upper limit is n, the lower limit is known. So, express the following using summation notation. 1 over n plus 2 over n plus 1 plus 3 over n plus 2, all the way up to n plus 1 over 2n. Any ideas how to approach that? Yeah. The index would be, say k. K is going from 1 to n plus 1. So, or we can have it as 0. So it'd be counting up n plus k on the bottom, in the denominator, and k plus 1 in the numerator. Does that work? Oh, they did I instead of k, but yeah. The general form of this summation can be expressed as I plus 1 over n plus I for each integer I from 0 to n. So I plus 1 over n plus I, where I is from 0 to n. The top index n of the summation is a free variable because it may be replaced by any integer greater than or equal to the bottom index, and each subsequent replacement leads to a different summation. For any particular summation, the top index acts as a constant. Thus, when the top index also appears in the terms of the summation, its value does not change from term to term. By contrast, the index variable in these examples is bound by the summation symbol. It must take every value from the bottom limit to the top limit in succession. Writing a summation in expanded form helps relate it to our previous experience of working with sums. But for small values of n, the expanded form may be misleading. What is the value of 2 to the 0 plus 2 to the first plus 2 to the second when n equals 1, or 0, 1, and 2? Now, when you evaluate a summation like this, you can avoid a mistake by imagining it in summation notation. So, I don't really see the point of doing it in summation notation when the expanded form is just addition. But when n equals 0, it would be 2 to the 0, which is 1. I guess you can see it helps you see where the n goes and the I goes and how it iterates. When n equals 1, it's 2 to the 0 plus 2 to the 1. And when n equals 2, it's 2 to the 0 plus 2 to the first plus 2 to the second, which is equal to 7. Using single summation sign and separating off a final term. Well, as a single summation, this is just n plus 1 added to, or 2 to the n plus 1 added to 2k from 0 to n. If you were to just make this to n plus 1, you could drop off that final term completely. So it would be the summation of 2 to the k from k with k equals 0 to n plus 1. Here, you can take off a term by saying the summation of 1 over I squared from 1 to n plus 1. You can make it 1 over I squared, 1 to n, and then add to it 1 over n plus 1. Yeah, 1 over n plus 1 squared, sorry. But yeah, just separate the last term and adjust the index accordingly. The starting and final, the ending index accordingly. In certain sums, each term is a difference of two quantities. When you write such terms in expanded forms, you sometimes see that all the terms cancel except the first and last terms. This cancellation of terms collapses the final result like a telescope. For example, observe that 1 over k minus 1 over k plus 1 is equal to 1 over k times k plus 1. Use this identity to find a simple expression for 1 over k times k plus 1. Well, you expand it out. You use the expanded version of it. You see it's 1 over 1 minus 1 over 2 plus 1 over 2 minus a third plus a third minus a quarter, etc. So the minus 1/2 plus 1/2 cancel. Minus a third plus a third cancel. So you're left with 1 over 1 at the beginning and minus 1 over n plus 1 at the end. And just all the other terms of the summation cancel each other out. Product notation. The notation of the product for the product of a sequence of numbers is analogous to the notation for their sum. The Greek capital letter pi denotes a product. For example, the product of a sub k with k from 1 to 5 equals a sub 1 times a sub 2 times a sub 3, etc. to a sub 5. If m and n are integers, and m is greater or less than or equal to n, the symbol here, read the product from k equals m to n of a sub k is the product of all the terms. So the expanded term form is this here. A recursive definition for the product notation is the following. If m is any integer, then if the summation of a sub k from m to m equals a sub m, it's just the one term. And a sub k, the product from k equals m to n equals the product of a sub k from m to n minus 1 times a sub n for every integer n greater than m. So the products, let's see here, 1 through 5, the product of k from 1 to 5 of k would be 1 times 2 times 3 times 4 times 5, which is 120, yeah. And then 1 to 1 is just the one term, so it would be 1 over 1 plus 1, or 1/2. So there you go. Properties of summations and products. The following theorem states the general properties of summations and products. If the sequence A and B are sequences of real numbers, and C is any real number, then the following equations hold for any integer n greater than or equal to m. Two summations with the same index and the same starting index and ending index are equal to the summation of the two terms added together. Likewise, a constant times a term in a summation is equal to the constant times the summation. And the product of two summations is equal to the product of, I'm sorry, not two summations, two products. The product of two products is equal to the two terms multiplied together in the product. So let a sub k equals k plus 1, and b sub k equals k minus 1 for every integer k. So what would the sum of a sub k plus 2 times the sum of b sub k from m to n, what would that be? Yeah. Expand it out by substitution, then bring in the constant, then add the two together, and then simplify to get 3k minus 1 summed from m to n. And again, by substitution and then simplification, you get the product of k squared minus 1 from m to n. Change of variable. Observe that this sum here is equal to 1 squared plus 2 squared plus 3 squared. Likewise, if you change the variable I to I, it is still equal to 1 squared plus 2 squared plus 3 squared. Therefore, these two summations are equal. The symbol used to represent an index of a summation is an example of a local variable, often called a dummy variable, because it can be replaced by any other symbol as long as the replacement is made in each location where it occurs. Outside of that context, both before and after, the symbol may have another meaning entirely. In the same way, a symbol used to represent a variable in a universally or existentially quantified state can be replaced by any other symbol as long as the replacements are made consistently. The appearance of a summation can be altered by more complicated changes of variable as well. For example, those previous summations could be written as j minus 1 squared summation from j equals 2 to 4. still equals the 1 squared plus 2 squared plus 3 squared, which was k squared summed from k equals 1 to 3. Transform the following summation by making the specified change. Change a variable, j equals k plus 1. Yeah? J equals k plus 1, so you could just substitute the k plus 1 for j here and make it 1 over j. And then k would be equal to j minus 1, right? J equals k plus 1, so your starting index would be 1, and your ending index would be 7. Yeah. Then the substituting for the k plus 1 is the j. So it would be the final, put the steps together and obtain the summation of from 1 to 7 of 1 over j. So rewrite the summation here so that the lower limit becomes 0 and the upper limit becomes n, but the index of the summation remains k. First, transform the summation by making the change of variable j equals k minus 1. Second, transform the summation obtained in part A by changing all j's to k. The index variable k is bound by the summation symbol to take values from 1 to n plus 1. When k equals 1, j equals 0. When k equals n plus 1, j equals n. So the new lower limit is n, and the new upper limit is the lower limit is 0, and the upper limit is n. Now n is a constant with respect to the terms of the sum. Unlike k, its value does not change from one term to the next. In addition, since j equals k minus 1, then k equals j plus 1. Thus, k over n plus k equals j plus 1 over n plus j plus 1. So the general term of the new summation is j plus 1 over n plus j plus 1. Therefore, your old summation here is equivalent to this new summation. Changing all the j's to k in the right-hand side of the equation gives this new result. It is equal to k to 0 to n of k plus 1 over n plus k plus 1. Factorial and n choose r notation. The product of all consecutive integers up to a given integer occurs so often in mathematics that it is given a special notation, factorial. For each positive integer n, the quantity n factorial, denoted n exclamation point, is defined to be the product of all integers from 1 to n. It is n times n minus 1 times n minus 2, etc., to 3 to 2 to 1. 0 factorial is denoted by 0 exclamation point, is defined to be 1. So the first 10 factorials, as you can see, the number goes up quite quickly. A recursive definition of factorial is the following: given any non-negative integer n, n factorial equals 1 if n is equal to 0, and n factorial equals n times n minus 1 factorial if n is greater than 1. Now, this recursive definition is useful for making computations. You can factor things out. So 8 factorial is 8 times 7 factorial. The 7 factorials cancel out, leaving behind 8. You don't have to do all the math and multiplying out 8 factorial and 7 factorial. Likewise, you can do some canceling out. Like D, n plus 1 factorial is n plus 1 times n factorial. N factorials cancel out, leaving behind n plus 1. So there you go. So C is, the 8 factorial is 7 factorial times 8 over 7 factorial, leaves behind the 8. On D, like I said, the n1 plus 1 times n factorial over n factorial, the n factorials cancel out, leaving n factorial. So an important use for factorial notation is in calculating values of quantities called n choose r that occur in many branches of mathematics, especially those connected with the study of counting techniques and probability, which we get into in Chapter 9. Let n and r be integers, with r being less than or equal to n, but greater than or equal to 0. The symbol here is read n choose r and represents the number of subsets of size r that can be chosen from a set with n elements. For all integers n and r, n choose r is n factorial over r factorial times n minus r factorial. In this chapter, we show how to compute its values. Because n choose r is always an integer, you can be sure that all the factors in the denominator of the formula will be canceled out by factors in the numerator. It is so common that many electronic calculators have keys for computing values. Those are typically labeled in one of these ways here. The letter C is used because the quantities are also combinations. Sometimes they are referred to as binomial coefficients as well, because of the connection with the binomial theorem. Use the formula for computing that to evaluate the following expressions. Well, you can see that multiplies out and cancels out all sorts of fun stuff, leaving behind 56. And B is just 1, because you have a group of 4 and you choose 4, you're going to choose you only have one option. And if you have n plus 1 options and you choose n, you're going to have n plus 1 options or possible combinations. Sequences in computer programming. An important data type in computer programming consists of finite sequences. They're usually referred to as one-dimensional arrays. Consider a program that analyzes the wages paid to a sample of 50 workers. Such a program might compute the average wage and the difference between each individual wage and the average. This would require that each wage be stored in memory for retrieval later in the calculation. To avoid the use of entirely separate variable names for all of the 50 wages, each is written as a term of a one-dimensional array. Subscripts are written inside square brackets in most languages. Some use parentheses. The reason is that it is, until recently, it was impossible to type actual dropped subscripts on most computer keyboards. And the index variable for a for next loop is a local or dummy variable. For example, the following 3 algorithm segments all produce the same output. For I equals 1 to n, for j equals 0 to n minus 1, and for k equals 2 to n plus 1, with the various subscripts and the array elements adjusted accordingly. Application. Algorithm to convert from base 10 to base 2 using repeated division by 2. A systematic algorithm to convert any non-negative integer to binary notation uses repeated division by 2. Suppose a is a non-negative integer. Divide a by 2 using the quotient remainder theorem to obtain a quotient Q0 and remainder R0. If the quotient is non-zero, divide by 2 again to obtain quotient 1 and remainder R1. Continue this process until a quotient of 0 is obtained. At each stage, the remainder must be less than the divisor, which is 2. Thus, each remainder is always going to be either 0 or 1. The process here illustrates the process for a equals 38. And you read the divisions from bottom up. The results of the divisions can be written as a sequence of equations. Yeah, like the in the format of the quotient remainder theorem, dq plus r. So then by repeated substitution, you can see that the remainders end up being used in the powers of 2 for each position in the number. Note that each coefficient of a power of 2 on the right-hand side of it is one of the remainders obtained in the repeated division of 38 by 2. This is true for the leftmost one as well. because 1 equals 0 times 2 plus 1. Thus, 38 equals 100110. In general, if a non-negative integer a is repeatedly divided by 2 until a quotient of 0 is obtained, the remainders found to be r0, r1, etc. to rk. Then by the quotient remainder theorem, each ri equals 0 or 1, and repeated substitution from the theorem gives this expression here. Thus, the binary representation can be read from equation 515. A base 10 is equal to r sub k minus 1, etc. to r sub 2, r sub 1, r sub 0. So do the process for 29. Repeated division gives these, and the remainders line them up in reverse order, gives you 11101. And here's the algorithm for the process. Feel free to explore this in detail in the slides on Canvas. You can use this algorithm to generate strings of binary numbers from decimal numbers. And that is it for the slide deck. So, I'm sorry? About 2 minutes. But yeah, that'd be it for the day. Like I said, it was one big long slide deck, and we'll get into section 2 on Thursday. In the meantime, have a wonderful day. See you next time.